Most of our mathematical careers, we have been solving problems from one dimension. But with calculus, we have opened up
shining, shimmering splendor.
Related rates are an application of derivatives, and they allow us to solve for one rate by relating it to another. Related rates play an integral role in our understanding of the universe, from the way planets orbit the solar system to...
Let's suppose there are two cars moving toward each other. Miss Estep is driving south towards Cougar Country at 10 meters per second and is 100 meters away. Miss Brown is driving west towards Cougar Country at 15 meters per second and is 285 meters away. 3 seconds later, what is the rate of change at which their distance is? We need to list out all the variables we know. We are given Miss Estep's and Miss Brown's initial positions as well as their velocity. So, Miss Estep's speed is 10 meters per second. Miss Brown's speed is 15 meters per second. Miss Estep's initial position is 100 meters away, and Miss Brown's initial position is 285 meters away. We need to figure out, what do we want to find? The overall goal of the problem is to find the rate at which the distance between the two teachers is changing 3 seconds after their initial position. We must first find the positions of each teacher from Cougar Country after 3 seconds by subtracting 3 times each teacher's speed from their original distances. So, for Miss Estep, that would be 100 minus 3 times 10, which is equal to 7. And for Miss Brown, that would be 285 minus 3 times 15, which equals 240. The Pythagorean theorem to solve for the third side of a triangle for their overall distance from each other. So the one side is 70 and the other is 240. So we just need to do 70 squared plus 240 squared. And this is equal to 250. We're almost done. We just need to use implicit differentiation on the Pythagorean theorem in order to find DC, which is what we're after. So we have a squared plus b squared equals c squared. We take a squared, the derivative is 2a dA. And that's going to be the same for all of these. So, we know all the variables except DC. We just solved for C. So we have A, we have B, we have C. Then we are given dA, which is 10 meters per second, and we are given dV, which is 15 meters per second. So we just need to plug in and solve. So we have 2 times A, which is 70, times dA, which is 10, plus 2 times B, which is 240, times dV, which is 15, is equal to 2C dC. So 2 times C, which is 250, times dC, which is what we want to find. Now, in order to find this, we just need to add all these up and divide by this. So, 2 times 70 times 10. Well, the easiest thing to do here is get rid of all the 2's. Then, we have 70 times 10, which is 70, plus 240 times 15, which is 3,600. So then we can add together 736 centimeters. So that is equal to 4,300. So 4,300 equals 250 DC. Now, we just need to solve this equation and we get DC. So 4,300 over 250 is equal to about 17.4. So DC is equal to about 17.4. And we've solved our problem. Solved this problem. It's time for you to do one yourself. And Mr. Ferraduti here will lead you through that one.
Anything but the face. Here, kids, let's get close. There's a phenomenon relating jokes in class to teacher likability. Hear me out here. Too little and you're a nobody. Too many and you'll lose the magic key. You need to make the perfect amount of political yet cultured jokes in order to achieve peak liking. The teacher likability index can be modeled on the interval. Ta-da! The perfect amount of jokes is pi over 2 jokes, and when the jokes per class is changing at 2 jokes per class. At what rate is the teacher likability index changing at this perfect answer, kids? Let's go. So first we have the teacher likability. Tx equals 20 sine x plus 1 on the interval 0 to 2 pi. And we also know that the perfect amount of jokes is when there are pi over 2 jokes and when the amount of jokes is changing at 2 jokes per class. So first, you take the derivative of the teacher likability index. So t prime x, which is going to be equal to 20. Now let's say it all together, guys. What's the derivative of sine? Cosine. Cosine x. Forget the x prime, guys. Now it's just a matter of plugging and chugging. So we have 20 times cosine of pi over 2 times x prime, which we have over here, is 2 jokes per class. So what's the cosine of pi over 2, guys? That's just 0. So anything times 0, we know is 0. So at this perfect amount of jokes, pi over 2 jokes in the class, the teacher likability index is not changing. That's going to wrap it up. How do you like a taste of your own medicine?
For a lot of important ideas, including you need to turn the word problems into something you can understand. Draw a visual. It's the easiest way to understand complex problems. Next, you also need to find a relation between the derivatives if one is not already given. Be creative, like similar triangles. Plug and chug. That's the most important.
Anyways, so in relation to other topics in calculus, the major premise of related rates are the use of implicit differentiation. So finding the derivative of an equation with multiple variables. Related rates can also be employed in optimization, which we learned, where you would need to find the highest or lowest value between 2 rates, such as 2 cars traveling. However, one is in the direction of a sine wave, for example, and the other in the direction of an exponential curve, right? So there's so many things you can do with related rates, only if you can imagine. Watching.